These are the things that we glossed over or skipped in the previous videos that we'll cover in this video. When we set up PID, we had to choose between independent or dependent PID implementations. We chose independent because it makes tuning the PID loop much easier. In the dependent mode, the error is multiplied by P, and in that is passed to I and D, which means every time you adjust P, you have to go back and adjust I and D. So I and D are dependent on P. This is how the old analog systems worked, where P was essentially the system gain, so every time you adjusted the system gain, it changed how I and D worked. If given the choice, you'll almost always want to choose the independent mode so you can adjust each parameter independently. While we're here, let's review these extra parameters that we didn't use in the previous videos. This one prevents the integral from getting too big. This is especially helpful when you have long integral times. For example, if I set the I parameter to 1 second and start the drive with PID enabled, we see PID forcing the drive to its max frequency to get the motor moving. And because the integral summed all of these large error values, the system pressure went way past the set point we wanted and then eventually settled out once the large values aged out of the sum. Now, since the normal errors are in the 3 to 4% range, let's limit the integral to 5% and run the test again. Now the integral doesn't get so big, and the system can react much quicker to changes. Now, while we didn't use it in our demos, this is something that you will almost always want to use in your system. And while there isn't a PID-specific lower frequency limit, you can limit the lower frequency using the drive's lower frequency limit parameter 626. Most of the time, you'll want PID to speed up or slow down the drive to compensate for load changes. It's rare that you'll want it to change the motor's direction. So this parameter limits the drive to only run the motor in one direction. That way, if PID goes nuts, your system won't be inadvertently slammed into reverse, which could damage a lot of things. If you do need PID to control both directions, then change this to a 1. Parameter 721 determines what the drive should do if it loses a 4 to 20 milliamp feedback signal. When the drive sees that there's no current flowing for a period longer than the time in parameter 720, then it can continue, ramp to a stop, coast to a stop, operate the last known frequency, or issue a warning and run at whatever frequency you put in parameter 722. This feature is turned off if parameter 720 is a 0, and of course it doesn't work on voltage inputs. The GS4 allows you to limit the PID output frequency. For example, when we start the drive, the output frequency goes straight to the full 60 Hz to try and force the motor to get up to speed as quickly as possible. But maybe you want to limit the stress on the motor or the system. If we set the max output frequency to 75%, then sure enough, the maximum output PID is allowed to use is limited. Of course, that also limits PID ability to perform, so it takes longer to achieve the desired result. The D parameter dampens fast transitions. You can see that in the spreadsheet from the previous video. We use these PI numbers, but look over here at the PID numbers. P is larger because we added D to dampen any overshoot. This is the step response from the previous video with only P and I. And this is the step response with the P, I, and D numbers from the spreadsheet. In our system, it really doesn't make a lot of difference, but it does start to introduce a little oscillation, so it's really pushing the edge of instability. The D parameter is usually not worth messing with in drive applications, but if you need to fully optimize your system, know that you do have the option available. We saw in one of the earlier videos that the feedback signal in our demo had a lot of noise on it. Why was that? There was a whole bunch of noise reduction techniques mentioned in Chapter 2 of the user manual, but none of those were the problem here. The problem was system design. If you look at this, the feedback sensor is located right next to a junction that was generating turbulence. It's also in the main flow of the water. By adding a stub pipe like this, you can get the sensor out of the main flow so it's not getting beat to death by the water. I wired the second sensor to analog input 2 so we can compare it side by side. For the record, I had to switch the terminal board switch for analog input 2 to volts, and I set up analog input 2's parameters like this. And look how much the noise is reduced simply by putting the sensor in a better location. The rule of thumb I like to use is to place a sensor at least 5 pipe diameters away from any turbulence generating junction. So if this is 1 pipe diameter, then we should place the sensor somewhere around here. But just for fun, I used this clear PVC so we could actually see what the water flow is doing. Here you can see the PVC flecks I put in the water screaming by, but down here, they're just gently floating around. So really, we probably could have put the sensor someplace up here and been fine. Now, one other thing I was curious about was how does this stub pipe get filled when it's empty? Well, here's the answer. It fills and settles out rather quickly. Cool. Now, when you do need to use filtering to calm a feedback signal down, make its duration as short as you can. Why? Because in addition to smoothing out the feedback signal, it also delays and slows down the process. Here we see one sensor with no filtering and the other with a 1/4 second filter we had in the previous videos. It does filter out the noise, but look how much longer it takes the filtered signal to reach its level. If we increase the filtering to 1/2 second, it looks even worse. And at a filter length of 1 second, the signal is almost unrecognizable. So be really careful when using filtering. Filtering should really only be used as a final tweak and as a last resort after proper system design and wiring has been done. Filtering really shouldn't be used as a total noise solution. Acceleration and deceleration ramps override the output frequency and make it difficult for PID to operate. For example, here's the step response from the last video, and this is what it looks like with a 1 second acceleration and deceleration ramp. Here it is with 2 second ramps, and again with 5 second ramps. The ramps completely destroy PID's ability to adapt to signal changes. Now, I know some folks use small acceleration and deceleration values to dampen oscillations, but honestly, if they're having to do that, then they probably didn't tune the loop right in the first place. The most common PID applications are integrating and self-regulating. In the last video, we did a self-regulating example. That's where when you run the motor at a fixed frequency, the feedback signal rises to a value and levels off. In an integrating PID loop, the feedback signal will continue to rise while the motor runs at a fixed frequency. For example, when filling a tank, the motor runs at a fixed frequency, but the fluid level continues to rise. It never levels off. I hope to do a video showing how to tune an integrating loop and a whole bunch of other PID examples, so be sure to subscribe to our YouTube channel so you'll be notified when those are available. Click here to learn more about the GS4 drive, and click here to learn about Automation Direct's free award-winning support options.